A great welcome to everyone. This is Nicola Marzari from the Institute of Materials here at EPFL. And it's truly both a great honor and a great pleasure to introduce today's speaker for one of the campus lectures of EPFL. EPFL is celebrating its 50th birthday, and so there have been during the year a number of very distinguished speakers from all over the world coming here and giving a lecture to the entire EPFL community. And also because today's speaker is so close to some of the topics we also explore in our Marvel NCCR. This will also be a Marvel distinguished lecture, so it will be filmed, and later on you can go and actually watch it again on the Materials Cloud. So today's speaker is Professor Giulia Galli, that is not only a friend from many, many years, but also very close to EPFL. Giulia is currently the Liu Professor of Electronic Structure and Simulation at the Pritzker School for Molecular Engineering at the University of Chicago, where she's also a professor of chemistry and a senior scientist at Argonne National Lab. Originally, she holds a laureate degree from the University of Modena and a PhD both in physics from the International School for Advanced Studies in Trieste. And after her PhD, she moved to Urbana-Champaign, working with Professor Richard Martin on the first ever ab initio molecular dynamic simulations of a liquid that was really the beginning of what became known as Carr-Parinello molecular dynamics, and in general this field of first principle calculations in the solid state. And after Urbana, and I have to say this was the first time I met Giulia. She came to give a talk to the Italian condensed matter physics community that had its annual meeting at Fai della Paganella in northern Italy. And I still remember that talk. Giulia moved to the IBM research laboratories in Rushlikon, and then actually here at EPFL, where for many years she was a senior scientist at IRMA, the Institut de Recherche Romande de Recherche Numérique et Matériaux, that really at the time I think was worldwide one of the most exciting and interesting places where to do simulations. In 1998, she moved to Lawrence Livermore National Laboratories. She created and headed the quantum simulation group there, again with many accomplishments in first principle simulations of materials, both at extreme condition, very high pressures, high temperature, developing novel methods. I still remember linear scaling quantum Monte Carlo, and linear scaling was actually one of the passions from the very first years, but also very many relevant applications to scientific and technological problems. She moved as a faculty in 2005 to the University of California, Davis, and then in 2013 at the University of Chicago, as I mentioned, the Pritzker School of Molecular Engineering, but she also directs one of the Department of Energy Centers for Computational Material Science, MICCOM, the Midwest Center for Computational Materials. Giulia has won many, many awards. I would just mention a couple that are very recent in the last year. The Theory Award from the Material Research Society, and the Ed Adler Fellowship from the American Physical Society. So with this, give me great pleasure to call Giulia, and thanks a lot for the title, also marveling at materials through in-silico lenses.
Thank you.
The floor is yours.
Thank you. Thanks, Nicola, for the very nice introduction, and thank you all for coming. It's always a pleasure to come back to EPFL, and in recent years I've had the opportunity to come back often because I'm part of Marvel's Scientific Advisory Board, and also because I like very much to attend SECAM workshops, and actually I was one here also for the 50th anniversary of SECAM not long ago. So what I would like to do today is to tell you what I called an atomic level stories about materials that have changed society or that are expected actually to change society due to the technology that have been built on those materials. So I will briefly introduce the materials that I have in mind, and then I will try to tell you what, in my opinion, theory and computation can do to understand these materials and really to be part of the discovery process that will eventually lead also to build the new technologies. And then I will tell you two stories about material for what I call sustainable energy sources. I will define this, and also materials that hopefully will lead us into the quantum information age. So let me give you two examples on which I think there will be no controversy of materials that have made a huge impact on our society. One is silicon. I think there are no doubts about that. You know, the transistor has been built upon silicon, although the first transistor was not built on silicon. And this is the cover of Electronics, a magazine at the time, 1948 in the United States, before Britain, Bardeen, and Shockley won the Nobel Prize in Physics for the transistors. And as we all know, this has given rise to, you know, what has been called at some point the digital age, and we have plenty of devices, phone that nobody really uses as a phone anymore, but you know, with many other, you know, in many other ways, and the also fastest classical computer. And other materials where I think there is no debate that have had an incredible influence are materials like lithium oxides, actually lithium cobalt oxide used to build batteries, and of course very recently the long overdue Nobel Prize in Chemistry was given to John Goodenough and to Whittingham and Yoshino. And you know, I took this picture from the website of the Royal Swedish Academy, and really there are innumerable devices powered by lithium-ion batteries. And lithium-ion batteries are part of the effort to really have a sustainable you know, economy and a sustainable materials by storing energy. But of course, we have to do, and much better than that. And we need not only to store energy, but to find the materials that will allow us to produce fuels that are cleaner than fossil fuels, not because we are running out of fossil fuels, but because we are kind of burning, right? And this is an old paper, in a way. It's 2013, but it's still one of my favorite. And the title is The Closing Door of Climate Targets. And it tells you, and there is a very, very nice analysis in this paper, the price of inaction. What happens if you don't act about lowering the emission rate of CO2 as a function of the year, and how much the temperature will rise? And the problem of finding material for clean fuel is related to the problem of water. This is a visual representation of what is now called water stress. It gives you an idea of countries where 50% of population, the red one, has not access to clean water. And of course, energy and water are related. But today I will concentrate on materials that people are thinking about for clean fuel. And in the second part, I will talk about the materials post-silicon that hopefully will take us to the so-called quantum information age. There is no winner yet, and maybe there will not be one a single winner. And I will tell you a little bit what people are thinking about regarding computing, sensors, and communication. And here, I've just put a plug for the center that we have in Chicago called Chicago Quantum Exchange, really devoted, and most of the people in these centers are experimentally, but we are also part of it, as other theoreticians are, devoted to understanding materials and processes for quantum information age. Okay, so as I said, what I want to try and tell you is how we can use theory and computation to be part of the scientific discovery process for the materials, especially for sustainable energy sources and quantum information that I just mentioned. And I will talk about specific type of computation. These are not the only one that you can use for materials, and the one based on using the laws of quantum mechanics and the laws of quantum mechanics in a computable form, so that we can simulate the behavior of materials at even different scales, starting from the atomistic scale. Okay, so this is a material in our view. So it's made of atoms, and atoms have positive ions, and then they have a glue, this kind of purplish thing here of electronic clouds keeping the material together. And of course, we know the equation. The equation has have been written down more than 90 years ago, and actually the paper signed by Schrödinger in 1926 was sent from Zurich. And of course, as we all know, we cannot in any exact form solve this equation, and so we have to do approximations. And this is a list of the major approximations on which calculation based on quantum mechanics are based upon. One type of approximation, so-called mean field theories, where the cloud of electrons that I told you about is described in an average mean field way, has been developed mostly in condensed matter physics, starting in 1965, around 1965. And the other big approximation are the approximation of quantum chemistry, which are based on one of the basic variables here, the wave functions of electrons. And then there are other type of approximation that came a little bit later, again, based on the basic quantity in the Schrödinger equation. So 1965, actually, around 1965 is the beginning of density functional theory. It's an exact theory. It takes 15, 20 years to have some approximation. Some have been written down very early, but some approximation that lead to a computable form of this equation. And the ability to compute really comes in the 90s. 1998, density functional theory and quantum chemistry are both recognized as very important fields in science, and indeed Walter Kohn and John Pople are awarded the Nobel Prize in Chemistry. And another important development, very dear to my heart, in 1985 is the development by Carr and Parinello in Trieste of ab initio molecular dynamics. So this is a coupling of mean field theory, density functional theory, with the solution of the Newton equation for the ions that are much heavier than electrons, that allowed people to look at finite temperature properties from first principles, and by that I mean no fitting to experiment, and also to thermodynamic property. And I really think that this method is one of the responsible for unifying at least a little bit the way condensed matter physicists and chemists have been looking at molecules and materials. So this is what first principle molecular dynamics is. We write down the second law Newton's second law, and we derive the interaction potential between all the atoms in the system from density functional theory. And I would claim that this is a very general predictive approach, although it has to be checked. And these are just pictures from my own work that I will mention also a little bit later. And we have used this kind of techniques, like many others, to look at assemblies of nanoparticles, for example, for solar cells, and materials for photoelectrochemical cells, and recently also at solids for neuromorphic computation and for defects for quantum sensors. These are not the only application. There are many others. I took this picture from a recent paper done here, and this is one of the works done here on energy storage, and in particular lithium-ion solid-state electrolytes. So how do we solve these equations? Of course, we cannot solve them analytically, and we need high-speed computing devices. This is how, in this paper by 1963, they were called by von Neumann. And it's interesting, if you read this paper, that he explicitly mentions nonlinear partial differential equations, which are the equation that we are solving when we are doing density functional theory. So as Nicola mentioned, I was fortunate to be part of the first simulations that were done on high-performance architectures, and especially on the first parallel computers. They were announced in the United States in 1993. I was actually moving to Lausanne at that time, and the first Cray 3TD was bought here in Switzerland and installed here in 1994. And for 5 years, between 94 to 98, there was a program of which I was part, and the simulation were headed by Professor Roberto Carr, who was the head of the group, called Parallel Application Technology Program, where we did one of our first simulation of first principle simulations. So actually our first simulation done on the Cray 3D was published in the EPFL Supercomputing Review. It was a simulation of diamond which turns into graphite. Of course, usually you would like to do the opposite, but for a number of reasons, we looked at that. And these were the planes of graphite exfoliating out of a carbon slab, and it was highlighted in this review here called Polyrama. I don't know if it is still there. And we wrote papers both in English here, general papers, and also papers in French, although all the accents were checked by somebody else, were not our own writing. We also ended up publishing in another journal a few years later, and where we described in details the interfaces between graphite and diamond. And to this day, I believe that although this may not be the most accurate simulation, the concept of studying interfaces from first principle is very important. The first author of the paper was Alessandro De Vita, my friend Sandro De Vita. He was a pioneer of this technique. He wrote the code, the first code that ran on the T3D in Lausanne, and he went on actually to be a pioneer of many other techniques, including some very popular today. And look, this paper is 2004, 15 years ago, about learning on the fly, and he was really one of the pioneers of these techniques way before many other people. Okay. So, if you do first principle molecular dynamics simulation, you can have a pretty good idea of the structural model of your material. You can have an idea of average property, especially if you're interested in ground state properties. Then what you usually want to do is to interrogate the material with light, to do spectroscopy. There are many names here, and these are not important, just to say that there are many techniques that you can use experimentally, and also by solving more complex equations than those that I just highlighted, you can also make contact theoretically. Not only that, you can go, this is taken directly from Wikipedia, by the way, you can go and do even more complicated spectroscopy looking at spin in the material, and this will become useful in a minute when I talk about quantum information science. So this is jargon that for the expert in the audience, if you want to do this kind of calculation and I really do spectroscopy, computational spectroscopy. There are a number of complex equations you have to solve, and also the challenge is really to build an integrated framework for multiple spectroscopy. So I mentioned codes, and the first code, actually it was called Lautrec, that ran on the T3D, and this was the first principle molecular dynamics codes, but for all the calculations, spectroscopy, spin, whatever, really having verified, validated, and optimized codes is successful. It's key to successful prediction, and my opinion is that open codes are really critical to innovation. If you want to innovate and if you want to ask your student and your collaborator to be innovator. And Nicola mentioned a center that is headquartered at Argonne National Laboratory, where we are working and developing codes for simulation. And there are actually 4 centers dedicated to this in the United States: Argonne National Lab, Brookhaven, Lawrence Berkeley, and Oak Ridge. And in spirit, although of course in the details very different, are very much doing work related to the work going on here at Marvel and also in the European Center, MAX. Okay, so now I hope I gave you an idea of the theoretical and computational strategy that we use when we look at materials at the atomistic scale. And now I would like to give you some examples of how we use these techniques, theoretical and computational, to look at specific problems. The problems in terms of sustainability that we have looked at and we are still looking at are problems related to solar cells, so materials that absorb light and generate electricity, and photoelectrochemical cells, materials that absorb light and use the charges created to do a chemical reaction. And then I'll tell you something about very old materials, diamond, back to diamond again, and also silicon carbide used for qubits and sensors. Of course, it's a little bit intimidating coming to Lausanne and talk about solar cells, right? So this is Michael Grätzel. This is one of the most famous paper, maybe in science, but certainly in the history of solar cells. And this morning I looked at how much time it was cited, 30,540 as of this morning. There is also a very interesting theoretical effort, for example, in the group of Ursula Lortilsberger. This is one couple, paper, both theoretical and computational, cited only 3,500 times, but it's not bad. And okay, so why are we still talking about solar cells? Because no size fits all, and not only it's not only a matter of efficiency. Of course, efficiency is very important. So this is a famous plot that is constantly updated by NREL in the United States that tells you about the cell efficiency. There are many different types of materials as a function of the year. And if you look carefully, you see here, people who started some fields, and you will read EPFL here, EPFL there, and in many other places. And they are all, these dye-synthesized and other still called emerging PV, although I would say that dye-synthesized solar cells have emerged pretty well. But so we have worked in this field and always together with our experimental friends, and in particular for many years with the experimentalist at NREL, National Renewable Energy Lab, and on quantum dot solar cells. The hopes there is that because they are easy to do and they are very tunable, you may be able to deploy them also in developing country where the manufacture of silicon and other solar cell is not that easy. So we have looked at ensemble of solar cells where we put together big molecules, nanoparticles, where we have both organic molecules that are attached to these nanoparticles and also inorganic molecules. And the question that we always ask is, given a certain structure, what's the function? Of course, one day we would very much like to go back and say, I want this function, tell me the structure, but we are not yet there. So, and using the method that I told you, both molecular dynamics, density functional theory, and also spectroscopy, we have been able to look at a number of problems related to absorption of light and also how you extract charges. And what we have learned, first of all, is that just looking at this nanoparticle that we and others have looked at for many years is not enough. And what you learn is, yes, the nanoparticle, the big molecule absorb light, but if you want to understand and make a new material, you need to design a nanocomposite, because these ligands actually form a nanocomposite with the nanoparticle. And one of our contributions has been to understand for specific system how to do that, and we have explained some experiment, and we have also made predictions that our experimentalist friends have verified. And this, I think, has been a success. We have proved, in some cases, that simplified model that you see in many papers in the literature like this, it would be great if we could have nanoparticles connected like this, are actually not even close to representing reality. And the first time we proposed this was, 5, 6 years ago, and we didn't get much traction at all. Actually, we got a lot of pushback in saying, this is not the model. But now, 5 years later, I think that, people are understanding a concept that, after all, is not very difficult to understand. There is a nanocomposite. There is just not only a nanoparticle. So if you want to absorb light to create charges and electricity is one thing. If you want to absorb light and use the charges to make a chemical reaction, to trigger a chemical reaction is much, much more difficult. And this is what you want to do if you want to build a photoelectric chemical cells, because your charges needs to be transported from the material that absorbed them, for example, to liquid water, if what you want to do is to split water to have fuel, hydrogen and oxygen. The reality is here. You have messy materials, so this is just one example. And if you look in detail, you realize that you have defective materials. You have, of course, to look at them at finite temperature, not at zero temperature, will not bring you very far. And you have very complex solid-liquid interfaces. So we have been navigating what I call the puzzle of water splitting for a while, and we have addressed problems in different parts on water, on interfaces, and the puzzle has not come together yet. So we have looked at the electronic property of pure and salty water, because you need to understand what the electronic levels of water are in order to understand how they are interfaced with absorber. We have looked at structural and electronic properties of interfaces. This is your electrode with water. And there is also excellent work done here, for example, on similar topic in Alfredo Pasquarello's group in physics. And we have looked at catalysts. This is a tough problem. But we have understood, and at least in some cases, how much it's not only the composition of your catalyst, of your material that triggers the reaction. It's the morphology that really matters a lot. And you have to look about active sites. And recently, we started looking at charge transport and how charges are transported around. And we also realized that even if we don't like it, and we would like to have a cell which works without any bias, there is always a bias that you have to apply because there is no material that does the reaction with zero bias. So we have started looking at also spectroscopy of interfaces under an electric field. So as I said, this is a big puzzle. We have bits and pieces. We understand quite a bit. There is a lot that we don't understand. And one of the major problems, although when I say we, I mean the community I work in, have made progress. Predicting catalyst is not yet something that we don't know how to do very well. So if you need some motivation about how much a catalyst can change life, here it is. This is the catalyst, which of course is not what we use today, discovered by Fritz Haber in 1908, that would combine atmospheric nitrogen and hydrogen from ammonia. So this is the world population as a function of the year. People were starving, and there is this lecture by Sir William Crookes at the British Association for the Advancement of Science, calling for scientists, say, please do something because we are starving. And this is after the Haber-Bosch process was invented, and this is the growth of the human population. So we do need a catalyst. We need actually several catalysts to have clean fuel. And if you need the motivation, this is a motivation. So predictive catalyst is what I would call a very complex problem. There are others that are always cited as outstanding open problems in material science. By no means the only one. One is certainly understanding and predicting high TC superconductor, and this for sometimes has become the poster child also of nitrogen fixation, and this is a protein with an active site that people don't know how to solve. So how do we solve these problems? And one idea is that you probably need a change of perspective. And that at least theoretically and computationally, you will not solve these problems on a classical computer, but you will solve these problems by going and build a different kind of ways of doing quantum computation, doing real quantum simulations on machines that are based on the laws of quantum mechanics. And one of the first lectures given, it's again an incredibly forward-looking lecture, was given by Richard Feynman at Los Alamos National Laboratory in 1983, where he talks about this, and he wrote a paper the year later, which I cannot claim to understand as many of Feynman's paper, but this paper lays out how to do computation, even the gates that you need, before even having anything close to a quantum computer in 1984. And everything is online, including all the lecture that Feynman delivered in 93. So basically, there are two principles on which we would like to base the building of the new machine. One is superposition, not only a bit, 0, 1, but a superposition of state, so we can build a qubit. And the other, of course, is entanglement. And sometimes when I present this picture, there are purists that tell me that this is not really correct. And yes, I know. But it's just to give an idea that if you untangle two states, they are intimately connected. And if you have an observation in one part, you affect what happens on the other part of the entangled state. So have we made quantum computers? Well, some people say yes, in the sense that, so this is a limiting error rate is a number of qubits. So some people claim that we will have a quantum computer when we can do error correction, okay? When there is no need anymore to worry about the fact that this entanglement is lost. But others say that, yes, we have some devices that can still solve problems that are also solvable classically. These are devices done in 2016 by IBM, Google, and here, probably you have heard about this. This is at the limit. Google announced a 54-qubit device and also announced to have reached quantum supremacy. I really have to say this. The word supremacy bothers me a lot, but it's used in quantum information science. They should have picked a better word. But anyway, quantum supremacy is I can solve a problem that is no way to be solved classically. And Google announced that they solved a problem that would take 10,000 years to solve classically. This is October 23rd. Actually, 2 days before the Google paper, October 21st, IBM came out and said, not quite. No. This is not really quantum supremacy. If you take Summit, supercomputer at Argonne, the one that I showed you in the first slide, you can solve the same problem by refactoring. And again, I cannot claim to understand in either 2 weeks or 2.5 years. I mean, there are some discussion of that, but anyway, it's not 10,000. And actually, Jay Gambetta came to Chicago and explained this to us for a couple of days, and yet I don't understand it. But anyway, the point that I want to make here is there is a lot of progress, incredible progress. Okay, so what are the challenges? Well, the challenges are decoherence of the quantum states and also error correction. I will not go there, but so you want to create a state, so you can create a coherent state, entangled state in an isolated system. But then when you have all the environment, usually the coherence after a while is lost, and then you cannot compute or do quantum sensors anymore. Okay, back to materials. So we have been working, again, in collaboration with experimentalists to look at specific materials where the quantum states entangled with each other are created in a solid, in defects that people like us and before us have studied for many years in solid state physics. And there is a defects in your materials, and especially the spin. They can be used to create an entangled state. People have studied diamond for quite a while. I show this picture because this tells you the kind of wafer that you can do if you go to silicon carbide, compared to diamond. And so there is a push to go beyond diamond just because how expensive and difficult it is to build. Using techniques that are based on the theoretical strategies that I told you about at the beginning, we have been able to compute this coherence time, how much these two spins stay in the states that we would like them to be without losing coherence that actually affects the whole device. And these are the kind of comparison between theory and experiment that we can have. This is too good to be true. And I don't think that this will be the same for all the materials, but it gives you an idea that we can get theoretically, and you can make prediction at least of the order of magnitude. This is good. And we can also make prediction about how these spins couple to the material, to the strain that is in the material. And recently, we have also looked at other type of materials, for example, two-dimensional materials where we have looked at this is the decoherence time, this is the concentration of the spins, and of course for two-dimensional materials you have to ask yourself how many layers do you have. So the dream, I would say, or the goal, depending on how you want to call it, would be to really be able to go from simulation of materials to quantum devices and back again. like in Middle-earth, for those of you who like Lords of the Rings, right? You want to go and back again. So this is the map of Middle-earth. So we would like to be able to predict materials and design them, and to the point where we also contribute to the discovery of novel computing and sensing devices. And if we have a quantum computer, we want to learn how to do quantum simulations. And if we do that, then we can go back again and predict even new materials, for example, for the other problems that I told you about, sustainable energy sources. And especially, in this era, I really want to also make a point about being careful about new technology, about the hype of new technologies, about how we deal with them. And again, a quote from Feynman, and this was 1 year before he passed away, after the, this was his testimony in Congress, United States Congress, where he said, for a successful technology, reality must take precedence over public relations, because nature cannot be fooled. And this is very important. So we need to be careful about talking about new technology, and we also need to be careful not making people believe that if we don't talk about climate change, it will go away. It won't, because nature cannot be fooled. So I talked about specific type of simulation and theory, and there are other type of calculation that I've not presented because I'm not an expert, but that I think are very important to predict materials and to realize the vision that I presented here today. And these are high throughput calculations. And here is an example of a work done here. It's a beautiful example of high throughput calculation to predict 2D materials done at Marvel in the group of Nicola Marzari. And this is another very important example of how we can use brand new techniques, totally different relative to what I told you before, based on machine learning, to do calculation based on density functional theory. And this is, again, I believe, a Marvel work which just came out in Chemical Science, done in collaboration between Clémence Corminboeuf and Michele Ceriotti. Okay, so I leave you with this question. We write a lot of papers, so we produce a lot of data. We want to use a lot of data. Where is the data? And how can we access it? We got very interested in this, and I know that here also Marvel is very interested in this. And we have worked a little bit on a way and on a tool to make data of scientific paper available, but I won't have time to discuss about this. I already talked quite a bit here. So let me thank my group who's responsible for the work of mine that I talked about, my collaborators, of course, funding agencies, and thank you very much for your attention. Of course, I'd be very happy to entertain questions. If it's not too late, sorry if I went over time.
I think we are perfectly on time, and indeed we have time for questions as well. I don't know if we have a microphone, but that's a different, oh, there is a microphone over there. And I actually have a question that is probably many questions for Giulia. What about the eureka moments in your life? That is, has there been a time when you sort of all of a sudden realize that this is it, something is happening that is really important and will change things?
I think that the eureka moment of my life are eureka moment after the fact. Usually, when I go back, I can trace back some thought of when I understood that something was different, was that, oh, this is not what we expected, this is different, we cannot explain this, or something where we thought we have to start thinking about in a different way. And then thinking back many years later, I could say, oh, maybe this was a eureka moment, but I cannot say, oh yeah, here is the new discovery. It's the process goes on for many years, and then you can look back and say, this was when things really weren't quite explained, and we were at the turning point of our research. I know that this is probably disappointing, but that's how I felt many times.
So thank you for the very interesting lecture. So as an expert in both experiments and theory, so I want to ask a very general question that how do you think, what's your perspective that what can combine these experiments and theory and eventually make the material happen? And with the advancements of the high performance computing, machine learning, and also advancement in the experiments. What's your perspective on this side?
Thank you for the question, a very important question. So I would say three things on that. One is looking at the future. When we get to do quantum simulations on quantum machines, the difference between theory and experiment will be very blurred. A quantum simulation will be an experiment, and it will be very blurred, and also in that respect, things will drastically change. Before we get there, also going back to the eureka moment, all of our, not all, but many of our results, specifically regarding materials property, were obtained because of very, very close collaboration with experimentalists, which usually started by trying to convince experimentalists of something, because usually it's not very easy to have them at the beginning listen to us, but then really going back and forth with them has brought us to our ability to predict at least some of the properties that we have predicted. I think that we have to automate this integration that we are getting to realize. There are very different ways of automating this. One certainly will go through AI and machine learning, but I don't have a very well-defined recipe yet. And especially, I don't think, again, that there is one size fits all. But I am completely sure of the importance of integrating theory and experiments to not only really to build and to make the device at the end of the day, but really to understand the parameters of the design.
Giulia, with the great success of machine learning, is there room left for scientific intuition? I'm sorry? Is there room left for scientific intuition?
Oh, of course. Oh, I mean, there is no... first of all, I am not the right person to talk about machine learning. I think that there are interesting things to do and to use and to learn about AI and machine learning, but I'm by no ways an expert. And there will always be room for scientific intuition. And I don't think that, you know, I don't even think that machine learning is killing scientific intuition. It's simply that the hype maybe is, but we'll go back to the ground state, and I think that we will find, I'm an optimistic person. I think we'll find good ways of using it. Behind you.
Thanks, Giulia, very much for a nice talk. I'm personally quite a lot concerned about climate change problems, and since you said you are very optimistic, I wanted to know your opinion. What is our future in the sense of climate change? Do you think we are going to solve it, and do you think public awareness is high enough for, or let's say, we put already enough effort to solve this problem, or you think we are still lagging back and we are destroying our nature faster than we actually...
Sorry, which I'm not sure I got...
the climate change problem.
Oh my God. So, what shall I say? So this is why I put the quote from Richard Feynman, right? The problem is that the scientific discoveries and everything that we are able to do will have to be combined with policies and with politics, okay? So that people understand how to deploy and how to foster scientific discoveries that are needed for climate change. Unfortunately, I'm not very optimistic, especially living in the United States at this point, on the problem of the policy. On the scientific side, if the right resources and the right push was put behind people, I think that we could make a lot of progress. And I think that the progress is slowed down by policies and politics at this point in time. I'm sorry to say.
I'll just take it. So since you mentioned that you are a big proponent of open simulation codes.
Oh, yeah.
I was wondering whether you could elaborate a bit on that, and maybe also on what kind of models you have in the States on supporting the development of open simulation codes.
Yeah, so we are basically trying to catch up with Europe in a way, in the sense that, for example, in our electronic structure community, most of the open source codes, and certainly the first one came from Europe. In the United States, the support of really working on codes, on open source codes, has started in 2015, believe it or not. It's very recent, and it's in 2015 when the centers that I mentioned, one at Argonne and the other three at other national labs, started, and we didn't have to hide anymore the development of codes. Having said that, it is of course, you know, it's not an easy job because for many reasons, including defining specifically which kind of jobs and how much the jobs that our students and postdoc will have after spending time developing codes, and this is, you know, a bigger problem in the universities and so on and so forth. But again, I wanted to look at the bright side, and yes, it started late, but it did start. We are making progress, and you know, one progress that we are making, and that is great in my opinion, is that because of the existence of these centers, there are a lot of experimental groups that are starting valuing our work more than before. And, you know, it's always the same. Say, oh, you know, funding agencies are putting money on this, you know. So they are starting to see our codes as their instrumentation, as they should be seen. And this has brought a lot of value. And I think that we are a little bit late in the game, but we are making progress, and there is progress.
You have mentioned high temperature superconductivity as a typical hard and unsolved problem. Now, as computational power increases, what would be your favorite strategy to tackle this problem? Doing more accurate calculations or doing a more systematic screening of possible materials?
you know, I knew that putting up these two slides, the nitrogen fixation and ITC superconductivity, I would be in trouble. The truth of the matter is I don't know. The reason why I put these two figures and two pictures that are used all over the place is because they have been picked by different companies, and the nitrogen fixation is specifically by Microsoft, and ITC superconductivity by some teams, by Google, and the grand challenges of quantum computation. I don't think that we are, and maybe Nicola would be better positioned to answer this question, but I don't think that we are even close to be in a position where we can do high throughput on ITC superconductor, and we are far because we don't understand the level of approximation yet that we have to put there. So we have a lot of, we have a long way to go. The reason why I put those two problems there is because every time you talk to the major company involved in or they give talks in quantum computation, these are the problems that are brought up. Unfortunately, I don't know the answer to that question, but high throughput, not yet, I believe.
Please.
Maybe you can shout, or I can repeat the question.
Goes and thinks about spin and spin properties and to build a quantum computer. Are we perhaps missing other opportunities?
Okay. So all the computers that have been built, which were in that graph, they are all superconducting qubits. There is no computer built with spin in solids yet. And especially within certain communities, people think that spin qubits will have a much bigger impact for quantum sensors. And then actually these quantum sensors, they may, revolutionize how we do NMR, dynamic NMR, and these kind of things, much more than quantum computing. And by the way, Feynman was talking about tiny machines, and if you see pictures of the quantum computer that they have built, and I've seen one at Righetti. Anyway, they are huge because they have these huge fridges to cool down their superconductors. So no quantum computer with spin yet, only superconducting qubits, and many people thinking about cold atoms as well. And so.
I think we'll take one last question.
I have a question about the quantum computing part. Is like, as far as I know about quantum computing, even if it is ideal with this, not the errors that are there, the answer that you get is probabilistic. And now when you have, so I was just wondering, like, do you see that in the near future we will be able to have quantum computers which will be able to do big calculations like we do with classical computers, like for example MD or DFT or something like really big of that sort, and if it is possible, like in how many years will something like that come?
So the papers that have appeared right now on the machines that are built with superconducting qubits, built by IBM and Google, that are problems that you can also solve classically, are just potential energy curves of molecules. They have solved this problem, and BF3 and these kind of problems. To go beyond that, and to go to a bigger molecule and to go to a material like silicon, and you need error correction. And we don't have any algorithm for error correction. Error correction meaning there will be errors caused by the fact that this property, the states are not coherent anymore. That's one thing. I have no idea, and unfortunately, again, I'm not an expert. I just repeat what I've heard in recent talks about how long it will take to do error correction. The Google paper, October 23, is without error corrections, and that's the problem they solved. There is a huge effort. Unfortunately, some of this effort is not public. For example, to try to solve on a quantum computer the equation of DFT. These are non-linear differential equation. On a quantum computer, it's much easier to solve the real Schrödinger equation, which is linear. There are, you know, if you go online and you read the blogs of what people can or cannot do, there is anything. But the only thing that we know for sure right now that has been at least peer-reviewed is that they could compute a potential energy surface of a molecule with 3 atoms.
Thank you.
Great, and I think it's time to thank Giulia for this wonderful lecture.
Thank you.
And I think also for the grace, the generosity, and the vision that was put forward. And I think you're all invited to an apéro behind here to celebrate. Thanks again, Giulia.